Good morning or good afternoon, everyone. I'm Haoran Yu, a PhD student from Rice University under the supervision of Professor Yin Lin. Today, I'm very excited to present our work, GCoD, Graph Convolutional Network Acceleration via Dedicated Algorithm and Accelerator Co-Design. The general background of this project is that Graph Convolutional Networks, or GCNs, show better performance on graph-based data than CNNs. In general, GCN includes two phases, aggregation and combination. As shown in the figure below, the first aggregation phase aims to aggregate the information of the neighbors, while the second combination phase will further combine the aggregated neighbors' information and node itself information. Although GCNs achieve good performance on graph-based data, recent breakthroughs on SOTA GCNs rely on massive graph data and computational power, making GCN inference very challenging. For example, as compared to CNN, GCN has prohibitive inference cost. A merely two-layer GCN model with 32 hidden units will require 19 G-flops to process the reddit graph, while a medium-scale CNN model ResNet 50 only requires 8 G-flops to inference on ImageNet. Then naturally, the question in our minds is why inference GCN costs so much? We attribute this to three reasons. First, real-world graphs are very large and irregular. For example, there are 230,000 nodes in Reddit graphs. We also visualize the adjacency matrices of null graph here, where one node may have many neighbor connections. That will result in evil rows in the adjacency matrix. Also, there are communities within the graph, so that the non-zeros in the adjacency matrix will be regionally clustered. Likewise, there are also least clustered regions, making the graph to have complex neighbor connections. The second reason is the extremely high sparsity within the graph adjacency matrix. For example, the sparsity in graphs often exceeds 99.9%, while the sparsity in sparse CNN only 10% to 80%. Such high sparsity and irregularity leads to workload imbalance problem during the inference. And the third reason is that the dimension of node feature can be very high. So efficient GCN inference has become a very important research problem. For efficient GCN inference, there are SOTA GCN inference accelerators, but they merely consider the accelerator design. For example, HyGCN proposed to skip zeros in adjacency matrix via window sliding. We show one example in the below figure. The workflow can be described as follows. First, we group the vertices or nodes within the same interval together, resulting in a grid from S11 to S44. Then we aggregate their neighbors' information interval by interval, meaning that we're sliding the window from S11 to S41. If there are no non-zero values in the window, then we can directly skip the corresponding computation or data moving. Another example is the AWB-GCN, which reduces the irregularity via auto-tuning workload balance techniques during runtime. As shown in this figure, the bottom bar denotes the row density in the adjacency matrix, while the upper bar represents the corresponding P utilization. We see that there are indeed unbalanced workloads. So to achieve more balanced P workloads, they consider three techniques: evil row remapping, remote switching, and distribution smoothing to make the workload distribution more smooth. However, there is one major limitation in both HyGCN and AWB-GCN. That is, they require large on-the-fly control overheads for reducing the irregularity. So how to overcome such limitation? We discussed the unexplored opportunity. That is, can we reduce the irregularity from the algorithm side by polarizing the graph adjacency matrix into workload balanced denser parts along the diagonal line, or workload light sparse parts along the off-diagonal line. Based on the unexplored algorithm opportunity, we propose an algorithm and accelerator co-design framework dubbed as GCoD. The motivation is to reduce the irregularity as well as boosting the efficiency and utilization. For GCoD accelerator, instead of following prior work, we consider to design a dedicated two-pronged architecture to cooperate with the exploit GCoD algorithm. Then naturally, there are two challenges in such a co-design framework. One is, on the algorithm level, how to enforce the regularity without compromising the accuracy. And another is on the hardware level, how to leverage GCoD algorithm for further boosting the acceleration efficiency. To answer those questions, in particular, we make three contributions in this project. We first propose the GCoD or graph algorithm and accelerator co-design framework. And on the algorithm level, we integrate the split and concurrent training algorithm to polarize the graph to be either denser or sparser without compromising the accuracy. On the hardware level, GCoD further develop a dedicated two-pronged accelerator with separated engine to process each of the enforced workloads. And next, I will elaborate on each point. This slide shows the overview of the proposed GCoD algorithm. As we can see from the visualization, the original adjacency metrics are very irregular, as the non-zero values are randomly distributed. While after adopting our split and concurrent training algorithm, most of the non-zero value will be aggregated along the diagonal line. Note that the diagonal line denser pattern includes different colors, while different color represents different classes. The workloads among all classes are also enforced to be balanced. And after enforcing such denser patterns, the remaining non-zero values are largely reduced and scattered along the off-diagonal line. Then we design a dedicated two-pronged accelerator for separately handling each of the resulting two levels of workloads. The intuition is very simple. If the mass irregularity is clustered into different classes, then we can leverage a dedicated sub-accelerator for processing the workloads of each class. That is corresponding to denser workload paths in the GCoD accelerator. And the general calculation includes two parts. The first part is the combination phase, where we multiply the input feature matrix with the weight matrix. And the second part is the aggregation phase. That corresponds to the multiplication between the adjacency matrix and the combination results. Such two steps will generate the partial updated features. Similarly, for the sparser branch, we also have two phases, while the combination result can be directly queried from the denser branch. But for the aggregation phase, we represent the adjacency matrix with the comprised sparse column or CSC format to indicate the, that is, we use row index and the column offsets to indicate the location of non-zero values. The sparse dense matrix multiplication will then be performed in a column by column format. And the generated features will be further combined with the partial results in denser branch to form the complete updated features. For GCoD algorithm, the challenge is how to reduce the irregularity. Our design insight is to polarize the graphs to be either denser or sparser by adopting the subgraph classification. In particular, we first cluster the nodes with similar degrees into the same class. As shown in the below figure, the green box and blue box represents two different classes. Then we divide each class into subgraphs of similar edges or workloads, so that different subgraphs within the same class can be accelerated using the same sub-accelerator. In addition, we consider an optional graph partition step, where the subgraph will be uniformly distributed into different groups. That can help to avoid to cluster dense area, so that can increase the reuse opportunity between denser branch and sparser branch. So how to make such design principle come true? We propose a split and concurrent training that includes 3 steps. The first step is to pre-train the GCN on partitioned graphs. where we first extract the subgraph class and then use matrices to partition into workload balance subgraphs. Based on such partitioned graph, we pre-train the GCNs using the cross-entropy loss, as shown in this formula, where Y is the ground truth labels and C is the prediction. The second step is to sparsify and diagonalize the adjacency matrix using the true regularization term as shown in this formula, where the objective is to optimize the adjacency matrix. The sparse regularization term will be 0 if the sparsity has met the target ratios, and it will be infinite if the sparsity haven't reached the target pruning ratios. As for the polarization regularization term, it will be the normalized absolute value between the subtraction of row index and the column index. So, and since these regularization terms are not differentiable, we follow prior work to use ADMM for optimizing them. The third step is the structure specification, where we prune patches where the number of non-zeros is smaller than the thresholds. And here we show the visualization of the generating results, where the first line is the original adjacency matrix, and the second line denotes the resulting visualization. We see that there are denser patterns along the diagonal line and sparser patterns along the off-diagonal line. Then we will go to the GCoD accelerator. And for GCoD accelerator, the challenge will be how to fully exploit the potential of GCoD algorithm. To tackle this challenge, we consider 3 design principles. The first one is the two-pronged accelerator that can separately process sparser or denser branches, which will be echoed with the GCoD algorithm. And the second principle is to discuss using gathered aggregation or distributed aggregation, since the aggregation phase is the bottleneck in GCN acceleration. And here we discuss 2 typical designs for accelerating the aggregation phase. The first one is the gathered aggregation. It executes nodes in a sequential manner. For example, here we first process the node 1 and gather its neighbor's feature in parallel. And then we move to node 2. The advantage of this design is that it requires only a small buffer for handling the aggregation results, thanks for the good reuse of the intermediate aggregation outputs. While the disadvantage is that such gathered aggregation causes irregular and frequent off-chip access of the weights and features, because that is often too large to be stored on chip. As an example, HyGCN adopts such gathered aggregation. The second one is the distributed aggregation. It executes the nodes in a parallel mode, while their neighbor's feature of each node are gathered sequentially for aggregation. The advantage is that the weight feature can be fully reused, since we process the adjacency matrix column by column. While the disadvantage is that it requires a large buffer to hold the intermediate aggregation results, which often cannot store on chip, and thus leads to frequent off-chip memory access. As an example, AWB-GCN adopts such design. Given that bandwidth is more limited when processing GCNs of poor data locality, we adopt the distributed aggregation following the AWB-GCN. And the third design principle is to consider a unified architecture. There are, in general, 2 designs. First is to perform aggregation first and then combination. In this way, the aggregation phase will be sparse matrix multiplication, while the combination phase will be dense matrix multiplication, so that it requires 2 different architecture designs for these 2 phases. Well, if we perform combination first, then both combination and aggregation phase will be sparse dense matrix multiplication. That can make the architecture design unified. And to make such design principle come true, we consider a two-pronged architecture design, which incorporates different accelerator design for denser branch and sparser branch. As shown in the upper part of this figure, the denser branch processes the enforced regular and the relatively dense subgraphs along the diagonal line in the adjacency matrix. Each subaccelerator here corresponds to one class and process the subgraphs within that class, while different subaccelerator process different classes. This is because subgraphs within the same class are workload balanced and thus can be accelerated using the same subaccelerator. For each subaccelerator, it includes buffers to hold input features, output features, weight, and index. Also, it contains sparse dense matrix multiplication units to handle in both the combination and aggregation phases. The sparser branch is shown in this bottom part of this figure. It at the same time handles the remaining irregular but significantly reduced sparse workloads, mostly on chip, according to a preloaded index information, benefit from the compressed sparse column format representation of the adjacency matrix. Also, we consider a query-based weight forwarding module that can enable the sparse subaccelerator to query the weights or combination results from the denser branch. Such query will be on demand, so that it can directly load from the subaccelerator in denser branch instead of off-chip memory. We summarize the characteristics of the GCoD denser or sparser accelerators here. As compared to unoptimized designs, GCoD denser enjoy balanced workloads, while GCoD sparser enjoy light workloads. Also, GCoD denser leverage multi-chunk architecture and requires more on-chip or off-chip storage. In contrast, GCoD sparser only have one subaccelerator and needs highly on-chip storage to store the index information. All our architecture can be reused by combination and aggregation phase. Apart from the architecture design, we also consider two fine-grained pipelines to further boost the inference efficiency. The first one is the efficiency-aware pipeline, where the combination adopts row-wise sparse dense matrix multiplication and generates one complete row at each time. While the aggregation is column-wise sparse dense matrix multiplication to spatially reuse the combination results and temporarily reuse the loaded adjacency matrix, generating partial results of the updated features at each time. The advantage of this pipeline is to maximize the data reusability, while the disadvantage is that it requires a large on-chip output buffer to store the partial results. In contrast, we have another resource-aware pipeline that performs combination column by column. By doing so, the aggregation phase can also reuse the combination results, as well as generating one complete column of the updated feature at each time. So the advantage is that it does not need a large on-chip buffer, while the disadvantage is that it needs more frequent access to the adjacency matrix. And here we summarize the characteristics of these two pipelines. In conclusion, row-wise pipeline aims to achieve maximum efficiency at the cost of more on-chip storage, so it fits more for small graph tasks. While the resource-aware pipeline make efforts to ensure that our GCoD accelerator can scale up to large graphs. Next, we evaluate the GCoD across 5 GCN models, 6 graph datasets, and use both the efficiency metric and accuracy metric. We compare GCoD against the SOTA baselines, includes both the accelerator baselines and algorithm baselines. Here we show the overall comparisons as compared to the SOTA accelerators. So GCoD achieve up to 15,000 times and 290 times speed up over CPU and GPU platforms respectively. If we use 8-bit designs, then it can achieve more aggressive speedups. And as compared to SOTA GCN accelerators, GCoD can achieve on average 7.8 times and 2.5 times speedups over HyGCN and AWB-GCN respectively. We also compare in terms of off-chip memory bandwidth consumption, where GCoD and GCoD 8 bits only require on average 48% and 26% off-chip memory bandwidth as compared to hybrid GCNs. And in terms of off-chip memory size, GCoD require much less, as low as 16 times and 60 times off-chip memory access reduction as compared to hybrid GCN and AWB-GCN. In addition, we perform evaluation of our GCoD algorithm. We see that GCoD algorithm can achieve such benefits without compromising the accuracy. In contrast, the accuracy even boosted. And we also provide the breakdown analysis of the GCoD accelerator. We see that after GCoD acceleration, the combination phase will consume most of the energy than the aggregation phase. That means the bottleneck of the aggregation are resolved in our design. Also, the energy cost of accessing off-chip memory remain reasonable when we increase the graph size. That justifies the good scalability of our design to support large graphs. So in summary, in this work, we propose the first GCN algorithm and accelerator co-design framework grouped as GCoD. And we adopt a split and concurrent training algorithm to polarize the graph without compromising the accuracy. On the hardware level, we further develop a dedicated two-pronged accelerator with separated engine to process each of the enforced workloads. And here is our contact information. So thank you for your attention. That's all for the presentation.